to get our solution in this biparts trigonometry question. We just integrate this, simplify, and then that'll be our solution. I won't bother doing it here, so let's move on. So now we'll work with Riemann sum and area, which is an application of integration in real life situations, or like in a function, however you call it. So with this is the graph associated with it, and if we plug 2 inside the equation, it'll yield 5. So that'll be our x coordinate and y coordinate, and then usually with integration, we'll write the integral function and then 0 to 2 for the x, and then write down the function dx, plug in our calculator, and solve for the precise area underneath the curve. In this, we get a really accurate solution, but then at times we also do like an approximation when we don't have our calculator, and that'll equal to 4.667. And there are 2 ways of a basic approximation called left and right Riemann sum, and then with that we usually work with a table if we're asked to do such an approximation. And in here, according to the textbook definition, what we work out to be the change in x would be b minus a divided by n, and then for the definition wise, b is equal to the upper limit, a the lower limit, and then n would be the number of sections or splits that it asks us to compute for the approximation. Normally, the more n there is, the more accurate our results would be to the actual value of the area underneath the curve. With right Riemann sum, we ignore the initial y value and then take the endpoint of each section to the right side as the name right Riemann sum, and that's the definition textbook wise. More on that later. I think it'll become clear once we have drawn the graph of it. Respectively, with left Riemann sum, we ignore the last y value and then we take into consideration the first y values of each split, so to say. And then this would be the definition textbook wise. Again, I'll draw a graph of left and right Riemann sum later, so to make it more clear. It's much more easy hands-on than the definition of the textbook, which is why I'm doing this lesson. Now that we have established the definition for left Riemann and right Riemann sum, we'll do an actual problem involving 4 stripes of the function x squared plus 1. So first we plot the x coordinates and y coordinate respectively, and then with that we kind of compute our left and right Riemann sum according to a definition, and I'll show how this is done. Personally, I feel it's easier to kind of conceptualize the definition of the two if there's like the actual graph to visualize the concept itself. So with left Riemann sum, this is our graph, so we plot the graph of x squared plus 1. That'll be the curve, and then since this is the left Riemann sum, we ignore the last y coordinate and stick with the first one. So the first one, this is our first cube, and then following that we establish the second one, and like this we finish the whole graph, drawing it starting from the left instead of the right, which is why it's called left Riemann sum. And as you can see from this 4 cube, which is from our 4 stripes, the area underneath the curve, the approximation that we made using this cube, is an underestimate. As you can see over here, there's some blank space not filled by the cubes. So with right Riemann sum, it's kind of the opposite. Excuse me. So for right Riemann sum, we start from the right and we ignore the initial y coordinate and then start from the right, and then we get this graph. And as you can see, opposite with the left Riemann sum, the cubes kind of protrude out of the graph, so this would be an over approximation. So this kind of a graph illustrates that with left Riemann sum we get an under approximation, and in a right Riemann sum we get an over approximation. But to prove it mathematically, we'll now compute the actual value of the left and right Riemann sum. Starting with the left, we input the change in x and then times it by the initial y value, and then we go down like this, and then that will be our whole equation, which solves for the area under the curve using left Riemann sum, and that would be 3.75, which as you can see is below the actual value of 4.67667 for our actual value. And then now we'll look into our right Riemann sum, and then different from the left, as I stated earlier, we'll also be working with the change in x, but in this case we're working with y values that's after the first one. So the initial one is ignored, and then we start the second one as we proceed down to the last y value, and that will yield us a 5.75. As you can see, this is an over approximation from our actual value of 4.667 that we have calculated using our calculator. So this kind of illustrates and proves that indeed left Riemann sum would be an under approximation, and that the right Riemann sum would be an over approximation of the function that we have calculated using the calculator. But this is specific to the case of our function x squared plus 1. In other functions, the left and right Riemann sum may be different. So at some it's an over approximation, at some it's an under approximation. It all depends on the function, and the best way to know if a left or a right Riemann sum is an over or under approximation is to graph it yourself, get a picture of it, and kind of graph the cubes, and then you'll know from the blank spaces underneath the curve or from the space that the cube protrudes the curve that the sum is under or over approximation. So now that we have established left and right Riemann sum, one might say, like, if one is over and one is under approximation, the sum of two may be a better approximation, and that's where comes the trapezoidal sum, in which trapezoidal sum, in essence, its value is actually the left Riemann sum and right Riemann sum's average. So if we see one as area 1 and area 2, it's area 1 plus area 2 divided by 2, and that would be our trapezoidal sum that approximates the value under the curve, and that will yield us 4.75, which is a lot closer than either left or right Riemann sum. But usually the test would tell you which sum to use, either right, left, or mid. But like statistically speaking, the closest one should be the trapezoidal sum. But more on trapezoidal sum later. We'll next move on to midpoint sum, and I'll draw a graph to illustrate that. There's actually a formula for it too. There is actually an equation that solves for the midpoint sum, and I'll do a graphical demonstration of that since I think it illustrates the concept better than just doing math. I'm kind of a picture guy, so over here we selected two splits, and in that we chose x point in between two x coordinates, and then take the y value associated with that midpoint. And then as you can see, like on a table wise, we did kind of the same thing as the graph over here, but here it's just four stripes, so that isn't really the important point, but it's just that the y value associated to the two midpoints is what we're using to solve for the area under the curve or of the function that we're trying to approximate. So this would be like the textbook definition of a midpoint Riemann sum. But personally, I think it's better to know how the graph look like than to just memorize the equation that's on the textbook, because that really demonstrates that you understand the concept instead of just memorizing the whole equation. And now we're on to our fourth type of Riemann sum, which is called the trapezoidal sum. This is different from left and right Riemann as well as midpoint sum, but some might confuse it with midpoint sum, but if you look at the graph, it'll seem clear that the two are not the same. The trapezoidal sum is kind of using the shape of a trapezoidal, if you can kind of visualize it, to approximate the area under a curve. And in that, I wouldn't even call it a stripe, because previously we were using things that's like a stripe or a cube, but this one is like using trapezoidal shapes to kind of approximate for the area for the of a function that we're trying to approximate for. And what I'm writing currently is kind of like the textbook definition of it. We need to pay notice that over here the 2f1 plus 2fx is just a middle value associated, which would be doubled if you're one that's concerning about the mechanics of the equation. But let's move on to graphing the actual fun stuff. So now we're still working with our previous example of x squared plus 1. We graph the curve, we plot the points, and then we kind of find a kind of like a linear line that connects the points. Over here I'm only using 2 trapezoidal shapes instead of 4 that I've used previously with the cubes, just for the sake of simpleness, and I think it also demonstrates the concept as needed. So over here we have the x coordinates, and then after we have drawn the line, we can set up for solving for the area of each trapezoid. And then as you can see, if over here it's actually a over approximation of our function because of the small protruding area of the 2 trapezoids. And then to solve for the actual area of the trapezoid, we find fx1, fxo, and then we find for the thickness of it, which is the change in x. Then with that we can kind of compute for the area. Over here, how do we solve for it? So that's basically f1 plus fo, and then we times that by the change in x, and we divide that by 2 to get the area of that trapezoid we're looking for. We do this for however many trapezoid we want to use to approximate for the area of the function we're trying to approximate for. And this is just the actual graphical representation of the equation I have written earlier, which solves for the trapezoidal sum of a function. And over here, and for our sake of our demonstration, we use 2 trapezoids, so we'll have 2 area associated with that 2 trapezoid. And over here I'm computing the area for the second trapezoid in terms of how it should be solved. Then now, since we have area 1 and area 2, we add them up together, and that would yield our trapezoidal sum of x squared plus 1 using 2 trapezoids in a trapezoidal sum, excuse me. And then what I'm doing right now is that I'm trying to combine the 2 areas, simplify them into an algebraic expression so that it'll be the same, if not similar, to the trapezoidal sum equation that the textbook had written to aid us compute for this approximation. And now, as I'm writing for the actual equation, I want to state that the same with left and right Riemann, as well as other Riemann sum, whether it's an over or under approximation, kind of depends on the function that you're given in an exam or in a test that you're working with. So the only way to be sure of it is to graph it yourself, and don't fixate yourself into thinking one is over approximation and the other is definitely under approximation. And as you can see over here, we have solved for the simplification, and then it's the same with the trapezoidal sum given to us in the textbook, with change in x equal to b minus a divided by n, and the 1/2, and then the midpoint 2 times to the middle y value, which in our case would be f of x1, and then we times it by 2 because it occurs twice. We use that y value twice in the 2 trapezoids we have, and as a result we have 2 of fx in our equation for the sum for the trapezoidal sum. And then if we have, let's say, 3 trapezoid that we're using to approximate for the area underneath this function, then as a result we'll have two y values that we'll be using twice in our 3 trapezoids. So in this case, the middle value would be always used twice, no matter how many stripes we use to calculate for the trapezoidal sum. This marks the end of BC trig identity and Riemann sum for BC calculus, and I enjoyed having class with you.